We need to finish up 4.4, and then we're going to start 4.5. 4.5 is on curve sketching. We're going to kind of take all the stuff that we learned about graphing and kind of put that together with some pretty interesting problems. So yesterday we learned about L'Hopital's rule, and then we were talking about some applications of L'Hopital's rule. So on this example right here, this is one where the textbook goes through this technique where we can change this from the indeterminate form infinity times 0 to, remember, L'Hopital's rule only works on a ratio of 0 over 0 or infinity over infinity. Okay, so we have to change it into that format. So the technique that this book wanted us to use was divide by the reciprocal of one of those functions. So we chose to divide by the reciprocal of x, which is 1 over x, which we talked about algebraically. That is the same thing as x times sine pi over x, and so forth. Went through and got the answer like that. But I wanted just to show you a different technique that I think in a lot of situations is a little bit more clear, even if you have to do a little bit more algebra to get there. So on this problem right here, you'll notice that this is the same, and I think I changed this in your notes after I printed it. Do you have a pi right there, or do you have a 1? Go ahead and put a pi there, okay? Yeah. So that it looks the same. So here's the technique that we're going to use on this one. So we're going to get the same answer. We're going to get a pi out of this. But here's what we do. Again, this tends toward infinity, and this one tends toward 0. So this is indeterminate form, but we've got to make this a ratio. So one thing that we can do with this is we can trade the behavior at infinity for the behavior at 0. So you'll notice that this quantity is infinity, and this quantity right there is 0. And when I say we're going to trade the behavior, this is what I'm talking about here, the starter question right here. You'll notice that both of these have a limit of 0. This is plain old x, limit as x approaches 0 from the positive side, and this is the reciprocal 1 over x, and we're taking the limit as x goes to infinity. So here's what we're going to do with this problem here. We're going to take this and we're going to trade the infinity for a 0, and we're going to do that by replacing every x with a 1 over x. So here's what we're going to do. I'm going to write limit, and I'm going to change this in just a second. Everywhere there's an x, I'm going to put a 1 over x. So that's going to be a 1 over x. That's going to be the sine of pi over 1 over x. Okay? Now, take just a second and look at that and convince yourself that if we were to algebraically move that around, it is the same thing. If we do this, approach 0 from the positive side. So let's just double check and make sure. So I'm going to simplify this expression right here. This is going to be the limit as x goes to 0 from the positive side. I'm going to leave this as 1 over x for just a second, and I'm going to write this as sine of pi x. Everybody okay there? Now, if I'm taking the limit as x goes to 0 from the positive side, this is 1 over a positive number that's getting smaller and smaller and smaller. So what's this overall quantity turning into? Infinity. Okay. I'm plugging in a 0 into this, essentially. The sine of 0 is 0. So this is in the same indeterminate form, but the nice thing about this is instead of worrying about the behavior way out on the positive end, we're just checking, hey, what's the behavior of this particular function as we approach 0 from the positive side? Okay? So it's the same type of thing, and the nice thing about this is going to be the limit as x approaches 0 from the positive side sine pi x over x. It's a little bit simpler format than what we were dealing with right here. And it's a little bit simpler as finding the derivatives also. Because if I plug in a 0, I get 0 over 0. Notice I've traded an indeterminate form where you can't use L'Hopital's rule for an indeterminate form where you can use L'Hopital's rule. So we're going to cite that we're going to use L'Hopital's rule. We're going to find the derivative of the top, which is pi cosine pi x over 1. And then we're going to take the limit as x approaches 0 from the positive side. So I end up with pi times, if I plug in a 0, that's a 0. Cosine of 0 is 1. So I end up with pi, okay? Now, I have found that on the majority of problems that I've run into, that I like that technique a little bit better, okay? If you like picking one of them, one of those functions and dividing by the reciprocal, the end result is the same. The only caution I'd give you is sometimes it's hard to tell which one you should divide by its reciprocal. So maybe on this one we tried dividing by 1 over sine of pi over x or something like that. Okay, it can get a little bit sticky. I found this to be, in the long run, a little bit more straightforward process. Change every x for a 1 over x, and change behavior at positive infinity for as x approaches 0 from the positive side. This problem right here, either way, works very well. I'm going to do this using the technique that I like. So what I'm going to do is I'm going to take the limit as x approaches. I'm going to trade behavior approaching positive or 0 from the positive side for positive infinity. That's a 1 over x, and that's an ln 1 over x. Let's see what we've got here, because remember, the reason we did this is this approaches 0. And what does ln of x approach as we approach 0 from the positive side? Think about ln x. Negative infinity. Okay, so it is in indeterminate form, 0 times infinity. Okay, we could check this one right here. This is still in indeterminate form. This is approaching 0. Okay, we'd have to stop and think about this one for just a second. Maybe we could rewrite this. Remember those logarithmic properties and stuff like that? Let's take this and let's change this around. Let's write it this way. Let's write this as the ln of x to the negative 1, and that's going to be over x. Why is that advantageous? Because you can bring that out front. So this is the limit as x approaches positive infinity, negative ln x over x. And let's just double check and make sure that this is in indeterminate form. Think about what negative ln x would look like. Ln x looks like this. Negative ln x would just be flipped upside down. So this would be tending toward negative infinity. The denominator's x, so it's tending toward infinity. So it is in indeterminate form. So let's find the derivative. So if I find the derivative of the top and the bottom, I get negative 1 over x on the top, and I get 1 on the bottom. So in the end, all I have to do is find the limit as x approaches infinity, negative 1 over x, and what is that answer? 0. Okay? I won't lie to you on this one. If you were to divide by the reciprocal of x, if you were to do ln x over 1 over x and do it that way, it works out as fast, if not faster. Okay? But a lot of times, if it's anything more complicated than this, figuring out which function you should divide by its reciprocal is kind of nasty. Okay? All right. Any questions? Okay. So let's take a look at the next one, and remember, L'Hopital's rule only applies to ratios, 0 over 0 or infinity over infinity, and yet we have all of these other indeterminate forms. So we're going to talk about how we can deal with those. Okay, so let's take this one right here. If I'm approaching 0 from the positive side and I have 1 over x, this is tending toward infinity. This is tending over, let's be careful here, the top is a 1. The bottom is, let's see, we're plugging in something really close to 0 from the positive side. This e to the x is a little bit bigger than 1 on the positive side of 0. So I'm taking a number that's a little bit bigger than 1, subtracting 1, so I'm getting a really small positive number. So I am subtracting infinity. Okay, so this is infinity minus infinity. If it were infinity plus infinity, what would the limit be? It would be infinity. Okay, that's not an indeterminate form. It's when we've got some magnitude of infinity minus some other magnitude of infinity. That's where we figure out, okay, well, which one wins? Okay. So the way we deal with this, yeah. Okay, think about what e to the x looks like. If you approach 0 from the right side, this number right here is just a tiny bit bigger than 1. So that right there is a little bigger than 1. We're subtracting 1. So this denominator, we've got 1 over something that's positive and getting really close to 0. So the limit would be infinity. Everybody good there? That's one way to look at it. I'm sure there are other ways to look at it. Okay. Anything else? Okay. So what we have to do here is, this is one of those indeterminate forms, but L'Hopital's rule only works on 0 over 0 or infinity over infinity. It only works on fractions, a single fraction, a single ratio. So what do you think we ought to do with this? Get a common denominator and add them together. Let's make our own ratio out of this. So that's what we're going to do. So we're going to find the limit as x approaches 0 from the positive side. If I get a common denominator, this one needs an e to the x minus 1. So that's going to be e to the x minus 1. This one needs an x, so that's going to be minus x, and our common denominator was e to the x, or sorry, x times e to the x minus 1. Now, did you follow the, I got a common denominator and I added those together all in one step. Is that okay with everyone? Everybody sees how we did that? Okay. Okay, now again, every time you transform this, if it was in indeterminate form before, it better still be in indeterminate form. So let's double check and see. If I plug in a 0, I've got, change colors here, I've got a 1 minus a 1 minus a 0. Top's a 0. That's good news. Okay, and if I plug in a 0 here, I've got 0, and then I've got 1 minus 1, so that's also 0. So I've got a 0 on the top and a 0 on the bottom. This is in indeterminate form. Okay. So this is 0 over 0, so I apply L'Hopital's rule. So that's going to give me the limit as x approaches 0 from the positive side. Again, no quotients here. We're just applying the differentiation rules to the top and bottom completely separately. So this is e to the x minus 1. And on the bottom, you could use the product rule if you wanted. If you wanted to distribute through, that would be okay too. But either way, you're going to have to use the product rule. You can't really get away from that. So I'm going to do the first times the derivative of the second plus the second times the derivative of the first, which is 1. We'll go through and do a little bit of simplification. And let's see what we get here. E to the x minus 1, x e to the x plus e to the x minus 1. Okay there? Should we apply L'Hopital's rule again? Maybe. We've got to check. Okay, we certainly wouldn't just blindly go through there. Plug in a 0, I get a 1 minus a 1, so I get a 0 on the top. If I plug in a 0 here, I get 0 times 1, so this is a 1. Sorry, take that back. That's a 0. And this is a 1, and that's a minus 1, right? So what's the denominator? 0. Denominator is also 0. Did we make any silly mistakes, or did we get this right? We don't want to apply L'Hopital's rule if it doesn't apply. We good? Got the derivative right, evaluated it correctly. So we apply L'Hopital's rule again. Okay, so we'll cite L'Hopital's rule, and here's what we get. Limit as x approaches 0 from the positive side. This is e to the x. So we're going to be done with L'Hopital's rule at this point, aren't we? Yeah, because the top's going to be a 1. Okay. And then I get, let's see, the first times the derivative of the second plus the second times the derivative of the first plus the derivative there. And the derivative of negative 1 is 0. So I get a 1 on the top, and I get a 0 out of this one, and I get a 1 here and a 1 here, so I get a 2 on the bottom, so the limit's 1/2. How are we doing there? Is that okay? Because I did the first times the derivative of the second, so x times e to the x, plus the second times the derivative of the first. So if I put times 1, that's just the derivative of this function right here using the product rule. Derivative of e to the x is e to the x. Derivative of negative 1 is 0, so I didn't write it. Okay? Mistakes? We okay? Okay. Chapter 3 was all about derivatives. That's where we learned how to find derivatives. And now we're flipping through derivatives. I mean, what do we find? Like 6 derivatives on this one problem? Okay. All right. Any questions there? Okay. Let's talk about some of these other formats right here. We're going to use a technique called a logarithmic limit. A logarithmic limit. And we typically do this when we have a function of x raised to a function of x. And there are 2 techniques for this. Pardon me. One of them is to take advantage of the fact that what we're dealing with here is a positive function. So I could take the logarithm of that function, and that would just give me the logarithm of the limit. Okay, that whole idea that I can apply a function to a function, still find the limit, as long as there aren't any domain issues or anything like that. The other thing you could do is you could use this identity right here that we've talked about before. I'm not a huge fan of this. I think the book uses this in a couple of instances. You're welcome to use that if you want. I kind of like this a little bit better. So here's what we're going to do. Okay, if I were to plug in a 0, okay, this is 0 for a denominator or something that's approaching 0. It never really is 0, right? And then the numerator is also approaching 0. So if I have 0 raised to the 0 power, that is an indeterminate form. So somehow I need to make a ratio out of this so I can apply L'Hopital's rule. So here's what we do. This is quite clever. Okay, we're going to take this and I'm going to say that the limit as x approaches 0 from the positive side of x to the 3x is equal to L. So I'm not sure what it is, but we want to find out what that finite number is. We're assuming that it's a finite number. I know this is positive, so here's what I'm going to do. I'm going to take the ln of both of these. I'm going to take the ln of this and the ln of that. And then I'm going to work on finding this right here. So this is the limit as x approaches 0 from the positive side. What does taking a logarithm do for me here? Lets you bring down the 3x. So this is what I'm trying to find now. And if I plug in a 0, I get 0. And this tends toward negative infinity, so this is an indeterminate form. So I could do a couple of different techniques here. I'm going to trade behavior at 0 for behavior at infinity, like we did before. So this would be the limit as x approaches infinity. This would be 3 times 1 over x, and this would be the ln of 1 over x. I'll show you in just a second. Okay. Yep. So we did something to put it in a form where I could work with it, and then we're going to go back and we're going to undo that process, basically. Okay. Any questions there? Okay. Correct me if I'm wrong, but haven't we done this before? Minus the 3. We did this one up above, but let me do it again really quickly. So this is going to be 3. Limit as x approaches infinity. This is the ln of 1 over x, which we chose to write this way. 3, limit as x approaches infinity, negative ln x over x. With me there? Wrote that as a negative exponent. Brought the negative exponent out front. Nice, easy format to work with, just like it was up above. I could even pull the negative out if I wanted to. I don't have to. If I plug in an infinity, this is negative, whoops, this is negative infinity, and this is infinity. So I can apply L'Hopital's rule. And this is 3 times the limit as x goes to infinity, negative 1 over x over 1, which is, better be the same answer we got before, right? Okay. This is going to turn into 0 times 3, so the answer on this is 0. Okay, now, is that it? It's not, okay? So I'm going to take this and I'm going to bring this back over here and be reminded that what we just found was, we found the ln of the limit we were actually looking for. If I took the ln of both sides and I worked on this right here with the ln in it, okay, I found the ln of the limit. The ln of the actual limit is 0, so how do I reverse this process? How do I undo taking the natural logarithm? Exponentiate with a base of e. So exponential base e and log base e undo each other, so that means the limit, I used a capital L to represent that limit that we were trying to find, equals e to the 0, which is 1. Okay, so that's the actual limit. Okay, again, logarithmic limits, kind of like logarithmic differentiation, are used when we have a function of x raised to a function of x. That property of logarithms allows us to bring it down, do some relatively simple algebra with it, okay, using those properties of logarithms, and then we find the limit, and then we just reverse that process. So we exponentiate both sides with the base of e. Any questions there? Okay, so if you flip to the last page, I'm going to do this last problem because this one's kind of interesting. This is just a calculus, just a classic limit problem from calculus. And maybe you've seen this before, maybe you haven't. Sometimes this will show up in a 1050 class or something like that. So here's how we're going to do this problem. If I plug in infinity, or the idea that x is getting larger and larger and larger, this is 1 plus something, some finite number, divided by a number that's getting bigger and bigger and bigger. So this is a 1, this approaches 0, but it's never actually equal to 0. So the base on this one is 1, and this gets larger and larger and larger. Okay? So if I actually had a 1 raised to the infinity, no matter how many times you multiply 1 by itself, it's still just 1. Okay? But if I have a number that's a little bigger than 1, say it was 1.5 and I raised it, or multiplied it by itself over and over and over again, it would get just ridiculously large. It would approach infinity. Okay? So this is an indeterminate form. The base is trying to drag this down and have the limit be 1. The exponent is trying to make this grow exponentially and get toward infinity. So we want to figure out which one wins. This is in indeterminate form. This is 1 to the infinity. Okay, and again, when we say 1, this isn't actually 1 because remember, this is just slightly larger than 1. Okay? So in order to solve this problem, we're going to do the same thing we did just a second ago. Oops, that's infinity. I'm going to take the ln of 1 plus a over x raised to the x equals the ln of the limit that we're actually looking for. So we're not sure what that is. We're not sure what this indeterminate form 1 to the infinity turns out to be. Good there? Okay. This is one where I really like using that whole reciprocal idea. I'm going to trade behavior at infinity for behavior near 0, which means everywhere there's an x, I'm going to put a 1 over x. But I'm going to be a little bit clever about this. I'm going to slide this out front to begin with. So if I normally have an x sitting out here, I'm going to replace that with a 1 over x. That looks good. And then I've got the ln of 1 plus, well, what would a over 1 over x be? ax. So here's what we're finding the limit of. X approaches 0 from the positive side. This would be the ln of 1 plus ax over x. Now, always double check yourself because this is a good way to make sure you did the algebra correct. If this is in indeterminate form, this should be in indeterminate form. So if I plug in a 0 in the denominator, I've got a 0. Good news for us. If I plug in a 0 here, I have 1 plus a times 0. That's 1. And what is the ln of 1? ln of 1 is 0. Okay? So it is an indeterminate form, so we're going to use L'Hopital's rule. And again, this is one that's pretty easy to differentiate. So this is going to be the limit as x approaches 0 from the positive side. The bottom is a 1. The top is a 1 over 1 plus ax times a. So I'm finding the limit as x approaches 0 from the positive side of a over 1 plus ax. Top's an a. Bottom has a 1 and a 0. So the limit is a. Okay, now that's the limit of the ln of the limit we actually want to find. So the ln of the limit we actually want to find is a. So what is the actual limit? E to the a. Okay. So sometimes you'll see this as a definition of the exponential function. Or if I put a 1 right here, if I did 1 plus 1 over x raised to the x and I find the limit as x goes to infinity, a would be a 1, So that would be the definition of the natural number e. Okay? So pretty wild that 1, something that's approaching 1, raised to the infinity, in this particular case, turns out to be e to the a. Okay? All right, any questions there? Okay, if I have time, I'll come back and I'll record a quick video about this. I'll just talk about this really quickly. This is not in this textbook. It's completely optional. We talked about this very briefly yesterday. This is L'Hopital's rule. It serves as a very good method for determining relative rates of growth. So in other words, if you have two functions and you knew they both went to infinity, you could figure out which one grows faster, okay, by using L'Hopital's rule and by using comparison. So let's just talk about this, and I'll fill this in, and then maybe I'll have time to record a video on this a little bit later. So if we have the limit as x goes to infinity of the ratio of two different functions, and the limit is infinity, okay, that means whatever was on the top grew fast enough to outpace whatever was on the bottom, okay? So this means f of x grows faster than g of x because f of x is bigger than g of x. That's the only way that the overall ratio of these functions could approach infinity, is if the top was bigger than the bottom. Does that make sense? Well, what if we do the same limit and we end up with a 0? What does that mean? Okay, that means g of x grows faster than f of x because so divide by bigger, put it in quotes because this is certainly not mathematically precise or anything, bigger gets 0, okay? So if I'm taking something and dividing it by something that's getting bigger and bigger and bigger, relatively speaking, we're going to end up with a 0. Well, what happens if I end up with a finite number like m? What does that mean about those two functions? Okay, so here's what we'd say. Grow at same rate. Now, you might say, well, what if this number is 7? They didn't grow at the same rate, okay? It's like 7 over 1. What we mean by when they grow at the same rate is there's a number that quantifies how big one is in comparison with the other. Okay? Okay? Because there is a number that represents how big one is in comparison. Let's see. Yes, you'd have a horizontal asymptote. Yep. Yeah. Question? Okay. Does it match up with this? Sort of? Okay. Okay. That's the idea. If I have time, I'll record a video that will go a little bit more in depth with that. Okay. Any questions there? Okay.